Well, hello and welcome to York's Observatory's TeleTube, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. TeleTube broadcasts on YouTube every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter with or Instagram with the handle at York Observatory and Facebook at Alan I. Carswell Obs. I am Matt, and I'll be one of your hosts this evening, along with Amin, Quinton, and Kat, broadcasting from the Alan I. Carswell Observatory located in Toronto, Ontario, Canada. Tonight, we've got a great presentation about binary star systems. You may notice this slide is a little bit different today. Actually, we have three fabulous posters created by the observatory members Noah, Bada, and Shannon, which are all celebrating the event coming up next week. That's right. Next week will be a little bit different because on February 18th at 2:30 p.m. we will be broadcasting a special event for the Mars Perseverance rover landing. Join us next week at this unusual time for a historic landing and hopefully the third successful mission to reach Mars this year. We will be live streaming on this very channel from 2:30 p.m. Eastern Time on a Thursday the 18th, not Wednesday like today. So make sure to tune in for this exciting event. But before we get started with tonight's event, with our main show, we want to give you a little update on what you can see this coming week. So tonight we can see Mars, which is the important protagonist of our future event, as well as Uranus and the Pleiades in the night sky. And if you have a telescope in hand right now, like right now, right at this minute, you will be able to notice a satellite passing by. As a matter of fact, you will be able to see Cosmos 405R passing in front of Capella and next to Aldebaran. And if you're not familiar with this satellite, well, I cannot blame you. I wasn't either. And it turns out it is a Soviet electronic and signals intelligence satellite launched in 1971 from the Plesetsk Cosmodrome in the USSR. And it was mainly used for surveillance and military purposes. But now, we may also not be familiar with another thing, which is the idea of binary stars. And as a matter of fact, there's a vast amount of binary stars in the universe, even greater than the number of single stars, we could say. Right now in our sky, we're able to see some of these binary star systems. On top of the region between Mars and the Pleiades, we should be able to find Chitauri, F Tauri, Lambda Tauri, Omicron Tauri, and others that consist of spectroscopy binaries as well as eclipsing binaries. Um, which will explain to you what they mean during this presentation. The names of these binary systems come from the constellation in which they are located, which is the constellation of Taurus, one of the oldest locations dating back to the early Bronze Ages, where it marked the location of the sun during the spring equinox. Aldebaran, the red giant we can see on this constellation, is the brightest star located here. It is also known as Alpha Tauri, and it looks really bright, doesn't it? As a matter of fact, it is actually the 14th brightest star in the night sky. Now, take that in account and imagine its size when I tell you that it is located really, really, really far away. It is actually 65 light years away from our solar system. And you guessed it, it has to be massive, right? So its radius is 44 times our sun's radius. But it is a cooler star than our sun with a surface temperature of only 3,900 Kelvin. And well, I think I'm getting a bit off of our topic, but why don't we get back to it by first defining what a binary star is, to later look at some of the most impressive and fascinating examples of these strange for us for sure, but common star systems in our universe. Go ahead, Amin.
Before we get into binary stars, I will explain what regular stars are. Stars are large astronomical objects initially made up of hydrogen and helium which have grown in size enough to have nuclear fusion occur in their cores. The energy emitted from the reactions in the core fuel the star, causing it to light up and to prevent collapse due to gravity. Due to the nuclear fusion, some of the hydrogen becomes helium, which then becomes carbon, and so on. Heavier and heavier elements are fused, as long as the star is large enough. There are several different types of stars. Our main sequence star, similar in size and mass to our Sun, is not large enough to go past carbon. These stars are the most common type seen, and they will end up as red giants at the end of their lives. Some stars can leave the main sequence and become supergiants. These stars will end up as incredibly dense neutron stars or black holes after they die. Finally, there are the dwarf stars, which are either remnants of bigger stars that have died or are just really small stars. A binary star is a system of two stars which orbits a shared center of mass. The two stars can be the same type as each other or different types and could be any of the possible star varieties. Stars are formed from clouds of dust and gas in space that are either made up of existing gas in space or from the remains of dead stars which exploded or ejected their outer layers. These clouds begin to rotate, and if they gain enough mass, they can collapse into a protostar. Once the pressure is high enough, due to the increase in mass, nuclear fusion can begin and a star is born. As for binary stars specifically, it is hard to tell how they form because of the difficulty in observing them at their early stages, but there are some models for their formation. The turbulent fragmentation model says that turbulence causes multiple clumps in a star core, which then each collapse to form their own star, and the created stars then orbit each other. The other main model is the disk fragmentation model, which says that gravitational instabilities in the disk of material that exists when a star is being formed causes another disk to be formed inside the first disk, and the resulting stars orbit each other like before. In both cases, something happens to the collection of matter that the stars are made from that causes a split. It may be possible for a single established star to capture a partner due to gravity, but this is thought to be very rare. Binary stars are of course composed of the same materials as regular stars. For a long time, it was thought that celestial objects outside of the Earth and in the universe in general were made up of something special, a sort of ethereal element or elements, which are different from the materials seen on Earth. After the advent of spectroscopy, where elements can emit light in a special pattern for each element, the composition of the Sun and other stars could finally be determined. The results showed that stars are made up of the same materials that exist on Earth. The average star is made up of around 87% hydrogen and 10% helium, with the heavier elements being only 3%. The larger the star, the heavier the elements created due to fusion in the core can be. Binary stars typically have the same composition in both stars in the pair as they were made from the same material cloud. After formation of the initial dust and gas cloud, a star can have a variety of masses. Initially, nuclear fusion creates enough energy to balance gravity and prevent the collapse of the star. In heavier stars, fusion progresses into heavier and heavier elements, ending at iron. Iron cannot be fused any further, and so large enough stars can eventually run out of fuel, and they become supergiants. When this happens, there is no longer outward pressure to counter gravity, and the star collapses. The outer layers fall inward and slam into the iron core, causing an explosion, which we call a supernova. If the star is not large enough to reach iron, it becomes a regular giant and eventually ejects its atmosphere. In this case, no supernova occurs, and this will happen to our Sun. Larger stars actually have much shorter lifespans. This is because their mass causes a higher rate of nuclear fusion. Even though they have more fuel to burn, the higher rate of fusion wins out. In a binary star, sometimes material flows from one star to the other, causing one to grow faster than the other. Sometimes one star is lost from the binary system due to external perturbations. The ultimate end result of a binary star can be that the two stars merge, or that both die out, for example from a supernova. There are several classifications of binary stars, and they are classified according to how they can be discovered. Visual binaries are binaries where the two stars can be both resolved and distinguished by a telescope. These binaries are typically close to us. The brightest star is given the A designation, and the dimmer star has a B at the end of its name. But most binary systems are too far away to be resolved by a telescope. They can instead be detected using spectroscopy. The spectral features of a binary system show Doppler shifts or changes in wavelength due to the movement of the stars. For this detection to work, the two stars have to be in the proper configuration, or the Doppler shift will not be seen. Eclipsing binaries are detected due to changes in brightness. In these binaries, one star can eclipse the other, blocking some of the light in the system. In this case, the brightness will periodically go up and down, which can also occur in intrinsic variable stars. Finally, the astrometric binaries have a wobble in their proper motion due to the interactions between the two stars, and they can be detected in this way. Around 50 years ago, binary stars were thought to be quite rare. Now we know that binaries are actually very common. Most stars that we can see turn out to have a partner. For nearby stars that are similar to the Sun, more than 55% have been confirmed to have double, triple, or higher partnerships. In general, NASA estimates that up to 80% of all types of star are actually multiple star systems. Recent models show that the magnetic fields of newborn stars are important to binary formation. There's a certain magnetic field strength which, when exceeded, seems to result in single stars forming. Below that level, the material cloud that forms the star fragments to produce a binary. Some physicists theorize that all stars are created in binaries, including our own Sun. However, our Sun and many others have no known companions, so this theory is not well supported. Some of you may have heard of the fictional star called Nemesis, which was once theorized to be a companion to our Sun that then abandoned it later. Unfortunately for binary fans, no evidence exists for Nemesis. Next up, Kat will discuss specific examples of binary stars.
Thank you so much, Amin. Now that we've delved deep into what binary star systems are and how they are formed, let us now look at and analyze some examples. What differs one star system from the other? How do we differentiate between them? I've queued up 3 examples, saving what I think to be the best one by far for last. To start us off, let's jump right into Beta Persei, also more commonly referred to as the Algol system, which is categorized as an eclipsing binary star system. It is approximately 90 light years away and is bright enough to be visible by the naked eye. The largest star, Beta Persei AA1, is a main sequence class B8, weighing in at 3.17 solar masses and 2.37 solar radii. The smaller star, Beta Persei AA2, is a class K2 type subgiant sitting at approximately 0.70 solar masses and 1.78 solar radii. There is a third star in the system, so why do we call it a binary system then? This is because Algol AA1 and Algol AA2 form an eclipsing binary pair as seen from Earth. More on this mysterious third star. It was named Beta Persei AB, about 1.76 solar masses and 1.73 solar radii. It is a class A star of A7M spectral type, about 10 times as bright as the Sun. AA1 and AA2 are separated by 0.06 astronomical units, and when they pass in front of one another, eclipses occur. A secondary eclipse occurs when the brighter primary star, Algol AA1, eclipses the lesser star, AA2, but can only be detected photoelectrically. One of the most important aspects of this particular system is that it contained one of the first non-nova variable stars ever discovered. Its discovery goes to Italian astronomer Geminiano Montanari in 1667. A non-nova variable star is defined as a star that suddenly pops into view, where early astronomers believed these types of stars to have just been born. This particular Algol is colloquially known as the demon star, and we can clearly see from the name that historians did not have quite a fancy for this system. But why? In Homer's Iliad, we come across the system when he writes, "The Gorgon's head, a ghastly sight, deformed and dreadful, and a sight of woe." The traditional name is of Arabic origin, which translates Algol to head of the ogre, and then translated back into English as the demon star. Still does not quite explain why such a vile name was used for a beautiful set of stars. Well, the star system is located in the constellation Perseus, located at the head of the celestial Medusa. It was also one of the 15 Bohemian fixed stars used during medieval times. It was associated with bad luck, violence, and misfortune. The odd part about Beta Persei is how its origin is unknown because there is no direct association with any other moving star group. But we do know that they formed from a cloud of dust and gas via gravity, but that is as far as our knowledge takes us. Next up, we've got the Sirius binary system. The system contains two white dwarfs that orbit one another, consisting of a main sequence star called Sirius A of either class A0 or A1, and another fainter dwarf of spectral type DA2, denoted Sirius B. Sitting at approximately 8.6 light years away, it is one of Earth's closest neighbors and will become brighter over the next approximately 60,000 years as it gets progressively closer to our solar system. It has an absolute visual magnitude of positive 1.42 and therefore approximately 25 times as bright as the Sun. Sirius B, on the other hand, is not nearly as bright, having been a red giant, and is significantly larger than its more famous counterpart. Their system is between 200 and 300 million years old, and originally composed of these two stars blue in color. Eventually, Sirius B burnt out more quickly than Sirius A, resulting in it becoming what we now know as a red giant. It then shed its outer regions and proceeded to collapse into a white dwarf about 120 million years ago. Sirius is also denoted as Canis, which implies the dog star, which perfectly exemplifies its presence in the constellation Canis Major. The heliacal rising of Sirius marked the flooding of the Nile in ancient Egypt, and therefore is documented evidence of its known presence in many ancient writings. What is odd about the pair of stars is that there is evidence of plain color controversy, whereas Sirius was said to have been reddish in color by Ptolemy of Alexandria in 150 CE. We can notice discrepancies such as these. They seem to have been very common, but for what reason we are unsure. It was also said to have been sea blue and then white in ancient China. The odds of there having been drastic changes to the star system in 3,000 years since the Roman period is highly unlikely, so we can scrap that idea right away. There could have possibly been differences based on the horizon line and the elements with which the light hit, portraying different hues of red, blue, and white. Something else that we can deem odd about the system is the potentiality for a third star. There have been some severe irregularities that were documented as of the late 19th century, but after some serious investigation, Hubble ruled out any objects that would have affected the periodicity of the system to that degree. So, what made the orbital period change so much? Well, nobody knows. Lastly, but most assuredly not least, we have Cygnus X1 that beholds a possible special surprise. Cygnus X1 is classified as a high-mass X-ray binary star system, located at just over 6,000 light-years from our Sun. It was discovered in 1964 during a rocket flight and emanated an X-ray field stronger than most ever to have been noted by Earth. The system is home to a blue supergiant variable star HDE 226868 that orbits another subject in question every 5.6 days. A stellar wind is produced by the star, and which provides matter for the accretion disk that orbits Cygnus X1. In examining the disk closely, one can note jets that are perpendicularly arranged on the disk. Cygnus X1 became what is known as the wager between Stephen Hawking and Kip Thorne when they were younger. Hawking believed that Cygnus X1 was a black hole, whereas Thorne disputed otherwise. In the 90s, the wager was settled as observational data was collected to strengthen Hawking's bet. It has become one of the most studied and important cosmological objects of its kind. If Cygnus X1 was indeed a black hole, the event horizon would be approximately 300 kilometers, and the super dense object is about 14.8 times the mass of our Sun. To elaborate on the evidence that proved Hawking correct, it was the discovery of the event horizon in 1992 through the use of ultraviolet observations on board the Hubble Space Telescope. It has to be noted that the radiation pulses that emanate from the core occur as a result of matter coiling into the gravitational singularity. The Cygnus X1 and HDE 226868 system have many similarities in terms of motion to a very large star, Cygnus OB3, which is about 6,500 light-years away. Astronomers speculate the possibility that both the star and the system formed in the same region at the same time. From here, I'd like to send it on over to Quinton, who will be discussing binary star system research and the potentiality for future endeavors therein.
Thank you, Kat. We've now seen many remarkable examples of these fascinating stellar objects, but the question remains, why do we study binary stars in the first place? Is it just because they're interesting, or are there more practical questions we can answer with this research? Well, first of all, binary stars are a great way to measure stellar masses. If a star is just sitting on its own in space, it can be very difficult to measure its mass. Sure, it is theoretically possible to measure a star's mass through gravitational lensing, which is carefully measuring how much light is bent by the star's gravity as it passes near it, but this effect is usually very small and difficult to detect. In fact, it wasn't until the 21st century that scientists were able to use this method to measure stellar masses at all. Up until that point, binary stars were the method that astronomers relied on to calculate the mass of distant stars. The key lies in the fact that the stars orbit around their common center of mass, and as long as only two stars are present, the precise paths they take over time can be predicted based on their masses, positions, and velocities at one point in time. This is known as the gravitational two-body problem. Okay, so we can analyze the orbits of binary stars and calculate their masses, but does that mean that the masses of orbits that aren't in binary systems are unknowable to us? No. As it turns out, there is a mathematical way of estimating the mass of a star based on its luminosity, or brightness, fittingly called the Mass-Luminosity Relation. In truth, there are several mass-luminosity relations, which each become valid at different stellar mass ranges, but it is usually easy enough to determine which mass category a given star fits into based on its spectral characteristics. This is usually just a question of classifying the star as a giant, main sequence star, white dwarf, and so on. These mass-luminosity relations were actually determined empirically by calculating the masses of binary stars through the previous method and then plotting these masses against the star's luminosities. The information we gained from studying binary stars allows us to discover connections between stellar mass and brightness in general, which in turn allows us to estimate the mass of all sorts of stars, whether in binary systems or not. If two binary stars orbit each other in such a way that they periodically pass in front of or eclipse each other from the perspective of the Earth, then they are called eclipsing binaries. As Amin mentioned earlier, as one of the eclipsing binaries stars moves in front of the other, it will block some of the light that the other star is emitting from view, causing a temporary dip in the total luminosity of the binary pair. Because their apparent brightness changes over time, eclipsing binaries count as a type of variable star, even though the actual light being emitted by the two bodies may remain constant. By measuring the time interval in between these luminosity dips, the orbital period of the stars can be determined, and the sizes of the stars relative to the radius of their orbit can also be determined based on the amount of time it takes the system to transition from maximum brightness to minimum brightness. As always, the masses of these stars can also be determined. But if the mass and size of a star is known, its absolute luminosity, or the amount of light it emits, can be determined by working backwards through the mass-luminosity relation. Well, so what? Didn't we previously use the luminosity to determine mass? Why would it be helpful to go the other way? The answer lies in the difference between absolute and apparent luminosity, and this difference can be used to measure the distance to faraway objects. Whereas absolute luminosity is a measure of the amount of light a star is emitting, apparent luminosity refers to how bright that star appears from Earth. We know that more distant objects appear dimmer than closer objects. More specifically, distant bright objects appear dimmer in a manner that scales with 1 divided by their distance squared. So if you have two stars with the same absolute luminosity, but one is twice as far away as the other, the more distant star will appear only a quarter as bright. For binary stars within our own galaxy, it is quite easy to convert between apparent luminosity and absolute luminosity, since the distance to other Milky Way objects are typically known to a great deal of precision. So it makes sense to use the luminosity to calculate the mass of other Milky Way stars. However, it can be much harder to measure the distance to objects outside our own galaxy, and this is precisely what eclipsing binaries can help us with. By comparing the absolute luminosity of these stars, gained from the mass-luminosity relation, to their perceived brightness from Earth, we can calculate their distance away in a manner that is 5% more precise than other methods. Since the distance to other distant objects is often expressed in terms of the distance to relatively nearby galaxies like Andromeda and the Large Magellanic Cloud, using extragalactic binaries to improve these measurements has the effect of making all sorts of other distance measurements more precise. There are some objects, called astrometric binaries, that look like stars orbiting around an empty space. The visible star can be seen moving back and forth like it would in a binary system, but its companion isn't visible. This could be because the companion star is just a lot dimmer than the visible one, and its light is drowned out, or it could be because the companion object emits very little light whatsoever. For example, a neutron star. Despite the fact that the other object can't be seen, solving the two-body problem still lets us deduce its mass. A similar effect occurs with exoplanets as well, although the wobble of the star is much harder to detect in these circumstances, as the planet tends to be of a much smaller mass than the star it orbits. This method of exoplanet detection, alongside transit photometry, which is the practice of detecting an exoplanet by observing a dip in the luminosity of its host star as the planet moves in front of it, has been responsible for 97% of all exoplanet discoveries. While we can detect exoplanets using a similar technique to what we often employ for detecting binary stars, an exoplanet orbiting its host does not count as a binary system. However, several exoplanets have indeed been found in binary star systems, although these discoveries are less common for binary systems than they are for singular star systems. It is unclear whether it is actually less likely for exoplanets to form in binary star systems, or if detecting an exoplanet is just a more complicated process in a binary system, and the difference is due entirely to sample bias. Well, some simulations suggest that binary stars tend to disrupt the disks of rocks and dust from which planets form, leading to a decreased probability of planet formation being successful. Other simulations predict that planets would in fact be more likely to form around binary stars, as the movement of the stars might help stir up the protoplanetary disk and improve the odds of matter clumping together in stable regions of the system. This is a topic that astronomers are still researching actively. If a planet did form in a binary star system, what would it look like? Is there any chance of it supporting life? Well, there are actually two basic orbital configurations that a planet in such a system could adopt: circumbinary and non-circumbinary. A non-circumbinary, or S-type, planet orbits around only one of the stars in the system. In order for such an orbit to be stable, the planet must orbit its host star at a much closer distance than the closest approach of the other star. The limit seems to be about 1/5. However, that doesn't mean the possibility of habitable S-type planets should be ruled out. The two stars that make up the nearby binary system Alpha Centauri are separated by a distance of 11 AU at closest approach, but their habitable zones are estimated to lie at a distance of 1.37 to 1.76 AU and 0.77 to 1.14 AU, respectively. There's no reason to believe a planet orbiting within either of those habitable regions would be unstable. The other orbital arrangement is the circumbinary, or P-type orbit, in which the planet's orbit encompasses both binary stars. Such a planet would effectively have two suns, much like Tatooine in the movie Star Wars. In order for this orbit to be stable, the planet must be located much further away from the stars than the stars are from each other. We've actually found an exoplanet, the gas giant Kepler-47c, that orbits within its system's circumbinary habitable zone, and there's no reason to believe that an Earth-like planet couldn't also form in a similar location. There could very well be extraterrestrial life on planets with two or more suns. We'll just have to keep looking. Well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Matt, Amin, Kat, and myself, Quinton. Make sure to leave any comments or questions in the comments section of the video and talk to us in the chat right now. We will be around for the next 20 minutes to answer your questions. All of our programs are free, but if you would like to make a donation, see our website at observatory.info.yorku.ca. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.